Am I audible? So, good morning. Am I audible? Okay, thank you. Good morning. So, today we will talk about congestion management. And first question is, what is congestion? Very first question is in terms of power industry or in the transmission network, what is the congestion? So, whenever there is a physical or operational limit of a network becomes active, so if we have a power flow limit, certain power flow limits in a particular line, if the line flow is reaches to that particular limit, the system will be called in congestion state. Our system is in state of congestion. Okay, so there are multiple reasons for congestion. Okay, so thermal limit is quite standard. This is one of the reason for the congestion. So whatever is the line is there, it has certain current carrying capacity, and that will decide the limit of the uh, line, and that will lead to the congestion if more and more power flows are happening through that particular line. Now, voltage limit also gives a maximum limit that potential difference is the reason for the power flow. And if the voltage difference is less, the power flow will be less as well. So even though let's say the line limit is higher, actual line limit, but it can only carry a certain amount of power, so you can also call it that it is also a congestion. Then there are certain stability limits, the angle, voltage angle, that also leads to the like we can operate within a certain band of the angle, so that will also lead to the power flow. And if that limits the power flow, the system may go into the congestion. So what are the different effects of the congestion? Okay, so first is market inefficiency and market power. So how will I define market inefficiency is a very basic example. Let me we had a example of a two bus system. We had initially we had example that certain generator is there. It has a cost of, let's say, $10 per megawatt hour, and another generator is here, and that has a cost of $20 per megawatt hour, and a load of, let's assume, 200 megawatts is connected here, and the maximum limit of this line is, let's say, 100 megawatt. So no congestion is there, which generator is going to supply so let's say this line limit is not present, so no line limit. In this case, the P1 will be 200, and let's say P2 will be 0. And if I talk about the cost, it will be 200 into 10, which is 2000. Okay, but with line limits are imposed, let's say, then we know that the P1 can it can transfer more power, it can produce more power, but because of the line limit, it will only give you 100 megawatts, and the remaining will come from the second generator. And then the costs are basically 1000 for the first generator, and then 2000 for the second generator. So this is 3000. Okay, so if you look at this particular exercise, so the market is basically looking for the cheaper options. Okay, and the if congestion is not there, it will basically go to a cost which is 2000 only, but congestion leads to a higher cost. Okay, so this is we can say that like market is inefficient, and like we talked about one deadweight loss example. Like we had a supply curve and we had a demand curve, and in this particular one, like the demand is kind of fixed, so we can say like if no congestion is there, the demand was 200 megawatt, and market clearing price for this will be 10. Okay, so if okay, let me not draw this. We have a like linear cost function, so I will draw it like this, that we have a generator which can produce 10, and the capacity is infinite, so it is going to infinite. So we have not placed any constraint on the generator, and then at infinity, so let's say the dotted lines are there, and at infinity we have a generator which again can produce another infinity, but at a price of 20, and this is the price of 10, and we have a firm demand of 200. So this is my demand curve, like it is a firm demand irrespective of the prices, it is going to consume 200. So I can say this is my market clearing quantity, and this is the point of intersection, so this will be the market clearing price, 10. But due to congestion, the first generator can only produce 100 megawatt. In that case, we have to draw another diagram. So like 100, and then at 20 goes to infinity. So it can only produce 100 megawatts at the rate of 10, and then remaining will be at the rate of 20, and we have a demand of 200. So the market clearing will be at this particular price, and the market clearing price will also be increased. Okay, so you can see the market basically is inefficient in this particular case, because the market clearing quantity is still same 200, but the prices has been increased. Now let's consider the similar example, like how the market can be inefficient. So let's say I have a generator here which can produce, let's say, 50 and 0, and the cost is $20 per megawatt hour. Okay, then I have a generator here again, it can produce 0 to, let's say, 300, and the cost is $10 per megawatt hour, and this is 200 megawatt. So if I again draw the, suppose these are the bits as well, so it can produce to 300 at the rate of 10, generator 1, and then second generator can produce 50 at the rate of 20. Okay, we have a demand of 200. So let's say this is my 200, and again the point of intersection will be this, and I can have that this is my market clearing price. But if let's say line limits are imposed, and it is 100 megawatt, in this particular case, what will happen that the first generator can only produce 100 megawatts. So this is 100, and second generator also has a limit, and it can only produce 50. So this is my mark. So like 10, 20, and the total demand is 200. So there is no basically intersection. So in this case, again we have to do some like management in this particular part, and what we will do is we will reduce this particular let's say because of some reason we have reduced this demand and cleared 150. So we are basically artificially reducing the demand, and if we reduce the demand, basically the social welfare reduce for the entire system. So that is basically market inefficiency. And in generalized way, if I talk about, we discussed deadweight loss, right? So some supply curve is there, some demand curve is there, and this was, let's assume that 200 market clearing quantity in unconstant parameter, and let's say this is the market clearing price. And because of the transmission congestion, let's assume we are only able to basically clear 150 megawatt. So we have reduced it. In this particular case, you can see this area was our deadweight loss. So this is basically loss in surplus. And by surplus means global surplus or social surplus basically. So this is basically market inefficiency. Another part was basically if you see market power. So how the market power is defined. So again, let's consider the same example which we have discussed here uh, in this particular one. So we can calculate the LMPs here. So like this schedule is there. Okay, with red pen, let me use. So with line limits, we have this particular schedule. Okay, and the cost are something 3000. Now, if I want to calculate lambda one, so it means I have to increase 1 megawatt here. Okay, and I will look for the cheaper option so that first generator will supply it. So the LMP will be $10 per megawatt hour. Lambda 2 is basically I have to increase 1 megawatt here, and I know that the first generator cannot supply because of the line limit. So now second generator basically sets the price, and the price will be whatever is the bid of generator 2. This generator basically has the market power, and market power is basically ability to influence the prices. uh, Jyotika, can you open the chat from there? Yes. So let's say instead of $20, if it increase, because this generator knows that this particular line will be congested for a higher load, and in that case he can ask that, okay, I'm going to instead of $20 per megawatt, my cost is 25 or 30. Then the LMP will be respectively, let's say the increased one 25 or 30 or so on, basically whatever he wants basically. So this is called market power. So congestion leads to market power, and market power is just for the timing, like it's a ability to influence the market outcome, and generally uh, market prices. So if it's a ability to affect the market price. So here is, like, what are the different effects of the congestion. So market goes becomes inefficient, and some players, like, in because of the congestion, one area will have market power. So what are the different features? So if I look at the, like, economic efficiency, so we have to manage the congestion. So, like, these are the regions and effects. So system operator will come into picture, and he will try to manage the congestion. So how we can manage the congestion? So some congestion management schemes will be there, some procedures will be there. We will talk about them, that how we can manage the congestion. But what should be the features of the congestion management scheme? So first is, congestion is there, we have to compromise with our market efficiency. We have to go away from our market, like true market clearing point. So in that case, the intervention which a system operator do to manage the congestion should be minimum. So that is like minimum or minimize the intervention, and so that very little deviation in social welfare happens. So that should be the objective. And generally, let's say if you are talking about a very short term aspect, to manage the congestion, we redispatch the generators. And as like with this particular example earlier, then when congestion was not there, the generator 1 was supplying 200, and when congestion was present, we said that okay, we will redispatch the generator. So generator 1's dispatch has been reduced and generator 2's dispatch has been increased. So that is basically generator redispatch. But let's say a congestion persists in a few lines uh, all the time or most of the time basically. So the long-term solution is basically creating new lines or generators. So if a corridor, transmission corridor is most of the times congested, it means we have to increase the capacity of that particular transmission corridor, which means we have to basically build new lines to relax that particular corridor. Another thing is, uh, what we can do is we can have more generators on the other side, so that if one generator is like, because of the, let's say, generation limit as well, because of the generation limit there will be congestion, because we cannot supply the actual demand. So in that case we need to build new generators as well. And usually like whenever there is a line congestion, we try to build generators on the opposite side so that the demand can be met. Another features are like very simple. It should be non discriminative, that it should not like affect a player more or less. It should be basically based upon the scenario. The effects on the player should be same. The method should be transparent, so all the stakeholders, like our generators, producers and buyers, they should be able to understand it, and they should be able to calculate that okay, this is how it has been obtained, like whatever congestion management has been done, so those decisions, and this is how it has been done. So the method should be transparent, and it should be robust as well, that it should nobody basically, let's say some method has been developed, and some players, if they basically able to manipulate that method, then those that method is not called robust. So nobody should be able to manipulate the congestion management scheme. Now there are a different classification, like some methods are non-market based, some methods are market based. So we will go them in detail. But first of all, let's talk about what are the different steps to check network accessibility. So first of all, we have to come up with the uh, or the calculate the ATC. ATC is basically available transfer capability. It is available transfer capability. Okay, based upon those available transfer capability, we will so that has been identified that okay, this much corridor or this much capability is available for certain transactions. Then we will look for the reservation, or we can say like contracts. So there are some existing contracts that okay, this power is will be injected by generator X and will be consumed by a certain buyer Y. So those reservations will also be the like input. And once it has been like ATC is calculated, the reservation has been identified, we will do the capacity allocation. So like based upon those reservation, we will impose that on the network, and we will provide that okay, this much capacity or capability is available to us, so we will allocate those, and entire thing will be done ex ante fashion. So like before the point of power delivery, we will perform this one. But let's say some after that, like for bilateral contracts or reservations, uh, some pool market or day-ahead market will like come into picture. So there will be some dispatch of the generators and buyers, that okay, this is going to be the dispatch. So we will include those dispatch, and then that our previous capacity allocation to the reservations, and then the new dispatch will be imposed on the network. And based upon that, we will forecast that these lines may become congested, or those lines will be congested. So we will identify where will be the congestion. Once congestion is identified, we will apply the congestion management scheme. And generally, these schemes have basically, like, first we will try to elevate the existing capacity. So whatever is the capacity of a line, how we can elevate that. So one is, like, redispatch the generator. So instead of, like, buying from a area where, uh, instead of, like, we have two generators example, so, like, instead of buying from generator 1, we will buy from generator 2, so that will relax the congestion, because now we are not buying from the generator A, which is making the system congested. We can perform counter trades. So, like, we can ask for the buyers to perform counter trades. So, like, power is flowing from A to B. So there was a transaction or trade happening between um, area A to area B. If we can basically, we can impose some counter trades, like from B to A, that will also relax the congestion. And the last point is basically, like, if some nothing happens, like with particular example I did, instead of 200 megawatt, we basically reduce the demand and curtail 50 megawatts of demand, so that we can able to supply that remaining 150. So that is the curtailment. So these are basically different steps to access the network. Now let's talk about how available transfer capability is defined and what is it is basically. So transfer capability is the measure of the ability of a interconnected electric system to reliably move power from one area to another over all transmission lines between those areas under a specific system condition. So there are many terminologies here, and we have to look those exactly. So it's basically, it is a ability that how much power are how much power can be transferred from point A to point B, and it is basically in an interconnected system. It's not like connections are only, like, point A to point B, there is only one line, so that is something else. But if interconnected power system is there, then what will be the, and like, how much we can transfer. Then reliability is another important, like how we can reliably move power from one area to another area over all transmission lines. So it's not like, the transmission lines between the 2 points, between over all transmission lines, and specified system conditions. So these are the few points, so, like, which we have to look at. Now this ability is limited by physical and electric characteristics of the system, and so available transfer capability, we will look at this differently, but let's see an example. We have discussed one example earlier, like, the three bus system. So I will go back to that system. So let's to calculate the transfer capability. Okay, what is the transfer capability? So let's assume a generator is here. We had this particular system. Another generator is here, and some load is here. So let's say this is bus number 1, bus number 2, and bus number 3. The maximum power flow of 1 2 is 30 megawatt. And let's not talk about these generators are present. So I am not considering there is any generator or load. Now, by looking at this, and other limits are relaxed, so I'm not going into other limits. Let's say infinite limits are there between 1 3 and 2 3. Okay. So if I ask you that what is the transfer capability from 1 to 2, how much power I can transfer from point 1 to 2, and let's say the reactance is same, uh, let's say 0.5 per unit, 0.5 per unit, and 0.5 per unit. So these are the reactances. How much power we can transfer from 1 to 2? Let me define these as well. Let's say 100 and 100. Anyone? How much power we can transfer from point 1 to 2? 1 is the injection point, 2 is the withdrawal point. Satya, how much we can transfer from A to B? Suman is saying 30. Any other answer? Suman, if 30 is incorrect, so actually I'm not talking about capacity. 50, 15, okay. So there are two terms, capacity and capability. Okay. Now let's look at more less than 30. Okay. So we are talking about capability, transfer capability. Now look at this particular definition. It's ability of interconnected system. If I say that only this line is present between 1 and 2 and the maximum flow of this line is 30 as defined here, in this case I will say that the transfer capacity is 30 only. Okay, that is completely true. But we are talking about an interconnected system. So this system is, I can say it is an interconnected power system. Now reliably move power from one area to another area. So the areas are basically 1 to 2. And reliably means like should not go beyond the limit of the line. So we can also say that 30 megawatt is the limit and we want to transfer 50 megawatt. So we cannot do so because it will not be allowed. So reliably we can only transfer 30 megawatt if it is not interconnected like this second case. Now we have to look at the power from one area to another area and specified system conditions. So I will talk about these 2 points later on. First of all, interconnected power system. So let's say if I'm transferring the power, so let's assume some power is being transferred from P1 and it has been withdrawn at P1. Okay, some P is there. So that if reactance is same, at 2 by 3rd of P1 will come on this side, 1 by 3 of P1 will come on this side, and then 1 by 3 of P1 will be coming on this side. So by looking at this, it is basically 2 by 3 of P1. So 2 by 3 of P1 should be equals to 30, and this will lead that P1 is basically how much? 45, right? So if I simply give you this particular network and if I ask you that how much is the transfer capability of the network, like if I want to transfer power from area 1 to area 2, how much I can transfer? So by looking at this scenario, I can transfer 45. Okay, now let's again consider that how much we can transfer. The same thing, the line 1 2 is limit is 30, and let's say this is 1, this is 2, and this is 3. So can you calculate transfer capability of 1 3? So this is basically 45. Now, how much can I transfer between 1 2 3 in this particular case? There is when there is no generator, no load, nothing is there. So Mohit is saying we can transfer 150. So let's see. So if I'm let's say transferring power from P1 from here and P1 from withdrawing P1 from here. So by looking at this thing, 1 by 3 of P1 will come here and 2 by 3 of P1 will come here and 1 by 3 of P1 will come here. Now, if you look at, okay, let's go back to this thing. It was saying over all transmission lines. That is very important part. So if I check, okay, let's go back to the previous example. So this line 1 2 is saying that we can transfer 45. If I look at line 1 3, it is saying that we can transfer 300, and line 2 3 is also saying that we can transfer 300. So but this line will be limited, so our transfer capability will be 45. The same method can be applied here. So here we can say that, like from the line 1 2 point of view, it will be 1 by 3 of P1, and that can only go up to 30. So P1 can be 90. If I look at the line 1 3 point of view, it is basically at 2 by 3 of P1, and the limit was 100. So it can be 300 by 2 is basically P1 can be 150. So line 1 3 can allow 150. Okay. And then line 2 3 is again 1 by 3 of P1, and the limit was 100. So we can basically allow it to P1 equals to 300. But this will be the, like if I look at the maximum capacities, this is the minimum I can transfer, because once I like once P1 becomes 90, this line will be congested, and then I can no longer basically inject more and withdraw more from the 1 and T. So I would say that transfer capability is 90 in this particular case. Okay. So then similarly, you can calculate for, like, let's say for 2 3, or the other way around, 3 to 1 or 2 to 1, you can calculate those values. So this is basically over all transmission lines we have to look at, and whatever is the minimum which we can transfer, that much is available transfer capability. Okay, so the line 1 2 has a capacity of 30, but if I am transferring power from 1 to 2, the capability is still 45, the case 1. And if I'm transferring power from 1 to 3, the line between 1 to 3 can allow 100 megawatt, but the capability uh, is basically constrained by the other transmission line or the entire basically interconnected system, and that will restrict that it can only transfer 90 megawatt. So that is the available transfer capability. So transfer capability, I would say, I am not going into available transfer capability. So it is a basically ability. So this ability is limited by physical and electrical characteristics. So these basically electrical characteristics are basically laws of physics. So we are following the laws of physics, and by laws of physics, we can only transfer that one line will also restrict the power uh, between two some other nodes. Okay, so that is one thing. Now, what is basically specified system condition? So certain conditions are there, basically, like our transfer capability. Does it mean that the lines are usually underutilized? We can say that for this particular example, we can say. And generally, like if you remember, like one blackout happened in 2011, and after that, like the complete India was in dark. That was because of overloading of a few corridors, and then outage of those corridor, and those outage leads to the, like the entire power move to another lines. Yes. uh, I will not call it underutilized, but yes, like we cannot dictate that if like 400 kV line of let's assume 200 megawatt is being built, so it should transfer, let's assume, like 80% utilization, and like 200 should be like at least 150 megawatt or 160 megawatt should be there. No, the other lines will affect the power flow in that particular line as well. So that is true. The entire system basically uh, defines the available transfer capability. Now, available transfer capability is something else. It is basically once a system is loaded. Okay, so it is again a measure of transfer capability. It is also a transfer capability, nothing else. It's the same, but the remaining capability is called available transfer capability. So remaining means uh, we have imposed certain transaction. So uh, some already committed users are there in the system, and then we are basically checking for over and above situation, that what how much more power we can transfer. So if I look at this particular example as well, let's say just to calculate ATC, let's assume now generators and loads in this particular one. So one generator is there, another generator is there, and certain load is there, and let's assume the load is 90 megawatt. Okay, so generator 1 can produce 45. So we I think solved this particular problem. So generator 1, if let's assume if I look at the cheaper generator which is 10, and let's say the expensive generator 2, so uh, cheaper generator will is basically between 1 to 3, and 1 to 3 how much is the capability is 90 basically, when there is no congestion or nothing at all in the system. Okay, so or nobody was present. So let's say still consider the same thing. So instead of 90, let's make it 60. So that 60 will come from the generator 1, let's assume, and 1 by third will go on this side, and 2 by third will come on this side. So 40 megawatt will come on this side, and 20 megawatt will come from this side. So these will be the power flows. Okay, so let's assume this is the situation right now, that 60 megawatt load is there, and these are the power flow. In this case, if I ask you what is ATC 1 2 again, how much is the available transfer capability between point 1 to 2? Anyone? So Satya, no again. So it's not literally the line limit. So I'm not asking line limit. I'm asking ATC between 1 to 2. So how much power I can transfer between 1 to 2? So we can say that a system is there. This 20 megawatt was flowing here, 40 megawatt is flowing here, and 20 megawatt is flowing here, and we are withdrawing 60, and we have injected here 60. Now I'm saying that I want to inject further power P1 and withdraw at point number 2. This is what I'm asking you, that what is the power transfer capability between 1 to 2. So this is what we are asking. So this is the existing system. So a commercial use is there, some users are already utilizing the network. Over and above this system, how much we can basically calculate. So if P1 is there, uh, some power will come here. So 20 plus 2 by 3 P1 will come here, and 1 by 3 of P1 will come here, and in opposite direction here, that will be the opposite direction, like the power will go here. So I will put a minus sign of 1 by 3 P1 here. Okay, and now if I look at to calculate ATC, I will first look at line 1 2, let's say. So line 1 2 is basically 20 plus 2 by 3 P1 can be maximum 30 megawatt. So in this case, I think you can calculate what will be the P1. Then 1 3, it is basically 40 plus 1 by 3 P1 can be 100. That is the line limit. Then line basically, if I talk about 2 3, it is basically 20 minus 1 by 3 P1 equals to 100. Is this clear so far? So yes, what will be the P1 here? 10, 10, 3, 30 by. So P1 will come that okay, you can transfer 15, And if I look at the line, this one, it's basically 60 into 3 is, uh, this is saying that 180 can be transferred. What will be the value of this part? It is interesting. It is very interesting. So yes, thank you. Okay, I'm going with you. It's minus 240, right? So this is saying that minus 240 megawatt can be transferred. So that is because we are transferring power which is opposite to the existing line limit. So we can say that, like, first of all, like if I increase P1, okay, and the power transfer between 1 to 2, and let's say if this line of this 15 megawatt constant is not there, this line 1 3 constant is not there, let's say infinity limits are there. So if infinity is there, they will go to the infinity, and like infinity if particular case there. And in that case the power transfer will be minus 240 for line 2 3. So basically 20 megawatt is going in one direction. We will start increasing P1. Okay, from the point number 1, we will inject the P1 and withdraw the P1 at the point number 2 or bus number 2. So first of all, we will overcome the existing 20 megawatt by supplying in the reverse direction. So those 20 megawatts will be like, first of all reduced to 0. Then we have 100 megawatt in reverse direction as well, the capacity. So that actually, like, if I not consider, let's uh, assume line 1 2 and line 1 3 have infinite capacity. In that case, the ATC in the existing scenario, like let's say 20 megawatt, 20 megawatt, and 40 megawatt are flowing, and I'm not basically deviating them. I'm that earlier it was calculated something. So ATC between 1 to 2 will be minus 240, or actually, like, the power is will be basically 240 megawatts. So I can basically inject 240 from the node 1. Okay, so I can inject 240 from the node 1 and withdraw 240 from the node 2, and the power flow in this direction will be, I think, 1 by 3 it is. So 1 by 3 is how much? 240 divided by 3 is 80, or it should be more. So we are looking at like 1 to 2, and if we look at the 2 to 1, then it is negative, negative, negative. So that's a tricky thing, that we are looking at line 2 3 from 2 to 3, but if we again, let's say, look at another line which is 3 to 2, then it will be like, the power flows will be 20 minus 1 by 3 P1, and the capacity is like, for this particular direction everything has to be positive. So whatever the power flow because of this transition 1 to 2 is happening, we have to consider the limit accordingly, and we will look at this particular formula as well. So the limit is actually minus 100 in opposite direction, and this is not correct, and it will lead P1 equals to how much? How much P1 is possible if I consider minus 100? 360, correct? So if this system is there, instead of 240 I can transfer 360. I have assumed that there is no limit here, line 1 2 and line 1 3. In this case, 1 by third of power will be flowing here, so instead of this 180 it will be 120. So, and no Satya, it's yeah, it's a 360. So earlier the power flow was 20, Now the opposite power flow is 120, and that resultant power flow like overall is basically 100 megawatt between from 3 to 2, and that is the our limit. So actually, like, let's assume line 1 2 and line 1 3 has no limit. In that case, the ATC between 1 to 2 is 360 as well, and it is far beyond the any limit or any line limit. So ATC is not restricted by the capacity. Did you guys understand this part, that it can be more than the line limits as well? So we had, like, certain line limits, and it can be more than that. Okay. So let's talk about again. Let me go back to the presentation. So ATC is a measure of transfer capability remaining in the transmission network for further activities. So over and above activities we are talking about, and over and above the existing uses. Okay. So we can define, or we can differentiate capacity and capability. So capacity is actually physical limit. Whatever, like, we have defined 30 megawatt, 100 megawatt, 100 megawatt. Those are capacity. Okay. So it is different from the transfer capability. And a very good example is basically highway. So let's say we have a 6-lane highway. So the car capacity is basically the lane size of the highway. That let's assume in one side it is 3 lanes, and another side opposite flow is 3 lanes. If I talk about, like, if it is a single one-way highway, I can only transfer 3 cars in one direction. So that is the capacity of that highway, that 3 cars can continuously go in that particular highway. But let's say at somewhere in the on the highway, one part or one lane is basically because of some accident, or because of, let's say, some, like, occupation, like किसी ने क्या बोलते हैं हमारा, वहां पे दुकान लगा दिया है ना, something happens, so some bottleneck is there at any point of the highway, so it will reduce the effective capability. So that has been reduced because some part of it has been utilized by somebody else. So that is capability, that yes, highway is still 3 lane, but because of some accident, one lane is not available. So that is existing uses of that particular lane to accommodate the accident, or whatever is our damaged vehicle after the accident. So the actual capability is only 2 lanes. So you can differentiate the transfer capacity and capability. So capacity is a physical property in isolation. So, like, if I take out the line, so in the 3-bus system we had certain lines. So if I take out line 1 2 and check how much power I can transfer from point A to point B, that is the capacity. So that for line 1 2 it was 30, and for other 2 lines it was, let's assume, for the particular example, 100 megawatt. So that is perfectly fine. But transmission capability is a collective behavior of the system, because the other lines are also affecting the my transfer between 1 to 2. Okay, that is one thing. Transfer capacity depends upon design only. That whatever is the, and, like, for that particular line, it is single circuit, double circuit, what is the voltage rating. So that design part of the transmission line will decide the transmission capacity, that okay, this much power it can carry. But capability depends upon design as well as topology. So the entire network will come, and system condition, that how much it has been already used. So what are the different system conditions? Even like, it's very complex, it's not that much easy, which, as I explained, so, we discussed two other parameters as well, like, voltage and security. So that also affects the, those are basically system conditions. So those also affect the capability. That capacity will remain constant because it's a isolation. So in isolation it will remain constant until unless, like, this pressure, temperatures, are like certain conditions are there. And capability is always varying. It will depend what is the system uses. Okay. And if voltage change, it will vary. If load changes, it will vary. If generation changes, it will vary. So it is always varying. So that's why it is time dependent, and the capacity is not time dependent. Transmission capacity is non-directional. Okay, so it is not at all directional, because if 130 megawatt of the line is there, in 122 it will be 30, and if 221 it will be 30. But if I talk about the capability, the power flows will dictate. So like we discussed, like in opposite direction, 20 megawatt was coming from 2 to 3 in the last example, and if we are transferring power in opposite direction of the 20 megawatt, the capability will increase as compared to the whatever existing system. So it is directional as well, like in which direction you are transferring the power. It is determined by the design. So whatever is the design, based upon that we can determine, and this will be determined through simulations. So like we have to put everything in the system, that okay, these are the system, now how much we can transfer. So by simulations we can only calculate it, and declared by manufacturer. So whoever is installing that particular line, he will decide, or he will declare that okay, this is the capacity of that particular line, and capability will be declared by the system operator, because he can only do the simulations, okay, needed simulations. So I think so far it is well understood and easy. Now let's see how we can calculate ATC. So there are different methods basically. Generally, the capability as well, we have some reliability margin, and also the line limits which we see is that okay, this is the line limit of a particular line. It includes different reliability margins, and different margins are already has been reduced. So actual line limit is always higher, okay, and the system can withstand a higher power flow, uh, whatever is given as compared to whatever is like provided by the system operator, but that is just to maintain the reliability. So we can go with the linear approximations as well, like because like if 1 or 2 megawatt go beyond the line limit, the system will still survive. Okay, so linear approximations are basically not accurate, but yes, we can adopt them because they are very fast to get the solution. Then if you want to go into like to calculate voltage and angle effects on the line flow, so in linear it will be only active power effects, and voltage magnitudes are zero, so only angles will play the role. Okay, but if we talk about like voltage and angles and like reactive power flows and all everything, then we have to go with the AC power flow model, and we have to identify certain sensitivities from there. Or we can do some like we can dump everything in a, system, and we can do some time domain simulations with a dynamic model. Okay, so this is how we can calculate ATC. So this part I think we already covered, like what are the assumptions for DC power flow model, what is the line flow in the DC power flow, and for a particular example we have written down certain constraints. Okay, so this we have explained that what is powers are equals to B, and then how we can basically get X, and based upon X, so this is what we have obtained as a X. And this as well we have discussed that what is the PTDF, power transfer distribution factor, and GSF. But to calculate ATC, we are going to need power transfer distribution factor. So this factor is basically uh, it is basically the uh, ratio of the change in power flow in a line to the transaction happening between point 1 to point 2. So ATC we always calculate that how much power we can transfer from point 1 to point 2. So this PTDF gives a linear sensitivity of line flow to point 1 to point 2 transactions. So this is the factor. And if I look at this, like this formula we already know, we have already derived it. So this is how we can calculate ATC using the PTDF. So let's say in a particular line some existing power flows are there, and then we will adopt um, we are injecting a new basically I can say this is a new transaction happening. So some initial transactions note are already there. Because of those transactions, some power is flowing in any line LM. Then we have basically a certain new transactions which are making between node I to J, and then we can calculate, like, based upon the power transfer distribution factor. If we multiply it, this will be the this factor is nothing but the delta power flow in line LM. Okay, so this is basically this part. Okay, delta power flow in line LM because of the new transactions which we are imposing. Okay, if uh, this will be the new power flow in the line. Now if you look at here, ATC is the power transfer between I to J. So this is basically ATC. So I can calculate this ATC. It is basically PF new minus PF note divided by PTDF. And ATC is the maximum available capability. So it is basically like if I'm transferring some power between I to J, how much maximum value it can take. So the maximum value it can take, so that's why I have placed maximum instead of new, and whatever is the line limit, we have used a PF max at the place of line limit. Now so this is maximum allowable transaction from node I to J, and constant. So but it is basically constant from one line only, like line between node I to node M. And we already discussed that it has to be considered over all the lines. So the ATC between I to J is minimum of this calculated transactions over all the lines. Okay, we also did earlier that, okay, we calculated for different lines, and whatever was the minimum, we defined that that is the available capacity. Okay, now let's not go into this. Let's discuss it like how can we use those particular formulas. So we had a 60 megawatt here, and 20 was coming from this side, 20 was coming from this side, and 40 was coming from this side, and we had a 60 megawatt coming from this particular side. Okay, so this is our base case. So I will name it base case. Okay, so this is my base case. Now I want to calculate ATC. So to calculate it is ATC, first of all we need a PTDF, and to obtain PTDF, we first of all we need the B matrix. So B matrix in this particular case will be, if let's we have assumed equal reactances. So X reactance, so it is like 1 by X, 1 by X, so 2 by X I think. Then minus 1 by X, minus 1 by X, minus 1 by X, minus 1 by X, 2 by X, minus 1 by X, and similarly 2 by X. Then what we have to do is we have to identify the slack bus, and we have to calculate a BR, which is basically let's say bus 1 is the slack bus. So this is, let's assume, the reference bus. So if this is the reference bus, I will put a 1 here and 0 different zeros here, and whatever is the 2 by X, minus 1 by X, minus 1 by X, and 2 by X. I think it is available in PPT as well. Let me see. Yes, here. So like for 3-bus system, we have this B initially, then we will calculate the B reduced. So B reduced will be calculated by this particular procedure. So we have this, and then if we take the inverse of B reduced, we will get a X reduced. So we will get certain X reduced like this. Okay, and then we will replace the reference comma reference equals to 0. So we have, instead of this 1, it has been replaced with 0. So this is our X matrix. Okay, so this is my X matrix available. Now with this particular X, I can easily calculate the PTDF. So like I will directly go X is nothing but 0 0 0 0 0 and it is 2 by 3 x, 1 by 3 x, 1 by 3 x, and 2 by 3 x. So this is what we have obtained. Okay. Now, what is the formula for PTDF? So PTDF LM comma IJ is basically capital X LI minus capital X LJ minus X MI minus X MJ divided by small x LM. Okay, and we have considered all the reactances equals to X. So let's calculate the ATC between, let's say let's calculate ATC between 1 to 2 first of all. Okay, so to calculate ATC 1 to 2, I will need minimization of power transactions maximum for all IJ and LM for the particular line LM. Okay, so for lines I have to take, so I have to take all the lines. So what are the different lines? So first of all, I have to calculate PTDF for all the lines. So PTDF line 1 2 comma 1 2, what will be this value? Then I will calculate PTDF line 1 3 comma 1 2. The transaction will remain same, so this IJ will remain same. Then we will calculate PTDF at 2 3 comma 1 2. So these are one way. Another is as well, like PTDF 2 1 comma 1 2, then PTDF 3 1 comma 1 2, and then we have PTDF at 3 2 comma 1 2. So these are the total 6 number of lines in both the direction if I talk about. So what is the PTDF? Can you calculate? So this is like x11 minus x12 minus x21 minus x22 divided by small x. So x small x12, and all like x matrix has been defined above. This is x matrix. So I will put everything is 0, and so it is 0 minus 0 minus 0 plus x22. It is 2 by 3x divided by x. So I can say it is 2 by 3. And if you calculate like 2 1, it will be minus 2 by 3, just opposite of that. Okay, so it's 2 1 is 0, 2 2 is minus 2 by 3, and 1 2 is 0 2 2, so it is minus 2 by 3. Similarly, I can calculate here like 1 1 is 0, minus 1 2 is 0, minus 3 1 is 0, plus 3 2. So 3 and 2 is basically 1 by 3 divided by x. So it is 1 by 3. So I can say it is minus 1 by 3, 3 1. Now what is 2 3? So 2 3 is 2 1 is 0. Then 2 2 is minus 2 2 is how much? 2 by 3. So it is 2 by 3x minus 2 1 is 0 and plus 2 2. Wait, I made some mistake, right? It's a 2 1 and 2 2. Then 3 1 and 3 2. 3 2 is 1 by 3 divided by x. So what will be this value? It's a minus 1 by 3. And if it is minus 1 by 3, thank you, Satya. The opposite will be 1 by 3. Okay. So once we have obtained these values, okay, I will. Okay, let me remove this part and simply keep it like this. That this is how we can solve it. So it's a so PTDF is similar to current division method. So in current division, it is basically, like you should know that one current is entering to a system, and it is basically the same current is exiting from the system, and then you can apply the current division. Yes, for this three bus system, we can assume or we can say it is kind of current division. But if we go more and more complex methods, we cannot apply current division method, like the actually the fundamental one. But yes, we I can say it is similar to current division, and because voltages are considered one, so currents are equals to power. So you are right, Mohit, that yes, it is similar to current division. But for complex method, we need a systematic approach how we can calculate it. So that's why the PTDF has been defined. So it is basically programmable and a systematic approach. So once PTDF has been calculated, I will try to calculate this particular formula. So it is PF max LM minus PF2. So I will let me write it down, that power transaction between IJ max was equals to power flow in line LM max minus power flow initial in line LM divided by whatever is PTDF LM comma IJ. Let me see if I'm written correctly. So yes, both are same. IJ, and that is only in line LM. So this is the power transaction which we are calculating for line LM. So I will try to calculate this part here. So you guys remember the network flow. Okay, you have to help me. I will not go up. So these are the flow like 20, 40 and 20. Okay, so now let's see. I want to calculate PT transaction was we are talking about the 1 2. What can be the maximum value, comma, line is also 1 2. So first of all, I will divide with the PTDF. So PTDF 1 2 comma 1 2 is 2 by 3. So it is positive. So whatever is the line we are considering, we will look at in the positive way. So the maximum capacity of line 1 2 is 30 and the power flow was 20. So this value can be 10 by 3 by 2 15. Then I can calculate the same basically 1 3 comma, sorry, ij is 1 2 and lm becomes, let's say, 1 3, and what can be the maximum value. So the PTDF is positive. So one more thing is, like a very if this PTDF is positive, based upon the sign of PTDF, I will use the maximum limit. So if it is positive, the maximum PF max will also be positive. If it is negative, I will use a negative limit. Okay, because it is another direction. So we are talking about line 1 3. Line 1 3 had the power flow of 40 megawatt, I think. So the capacity was 100 minus 40. So 60 by 16 to 3 is 180. Similarly, we can calculate the PT for the same transaction, and line is 2 3 max value, and we can calculate the PTDF is 1 by 3 here. That is very important. It's 1 by 3. So if it is 1 by 3, it's negative. So I will use a negative limit here. So we had 100. Instead of that 100, I will use a minus. And the direction 2 3 we are considering. So in 2 3 direction, the power flow was the same, positive 20. So it will become how much? Minus minus plus 240 or 360? 360. Yes, thank you, Satya. Similarly, let's say if I want to calculate PTDF for transaction 1 2 and the line is 2 1, opposite direction. Okay, so this PTDF is minus 2 by 3. We'll consider the line flow as a negative, and it is talking about line 2 1. So line 1 2 and 2 1 has the same capacity of 30. So I will use minus 30 minus power flow is basically line 2 1 direction. So what is the line 2 1? in opposite direction, so the power flow will be minus 20 here. So what will be this value? Same 15. So yes, it is 15. But so if you see, like both these values are coming 15. The for line 1 2 or line 2 1 as well. Okay, because the transaction is happening in one direction. So even if we have considered the reverse of the line, the power flows are coming the same 15. Similarly, if I go like the same next part, like this part for PT max, transaction is 1 2 and line is instead of 3 1, so it is again negative minus 1 by 3. So if it is minus 1 by 3, line 3 1, so I will put minus 100 minus, and the line is instead of 1 3 it is 3 1, so it is minus 40, and that will be equals to basically 180. And similarly, like PT max for 1 2 direction and 3 2 line, so 3 2 is 1 by 3, so I will consider positive line limit minus, but the power flow will be reversed. So I'm talking about 3 2 line, but actual power flow in the line is 2 2 3, so that's why the line flow will be minus 20, and that is 360. So everything is basically same at the 15 180 and 360. Okay, so now ATC is basically minimum of all these. So ATC for line 1 2 is minimum of all PT max we have calculated for 1 2 and for all lines LM, so that is 15. So this is much we can transfer. If you have any doubts so far, please ask. We understood this part with the concept like earlier, and now what is the systematic way of solving it? Any doubts so far? uh, Yesterday in the group basically we were discussing about certain books, so just to inform you that I shared, okay, wait, something, okay. So we discussed that like I put the quiz will be on Sunday, available from 8 in the morning to 8 in the evening. But again, the time, like once you start it, you will have a limited time of either 30 or 40 minutes. So uh, start it when you are well connected and free. That is point number one. Another thing is the like timetable class lectures I have placed already. We are not following the timetable which we have provided earlier, like because of something like some lectures has been shuffled, but we will try to cover the entire syllabus. And about the books, I have shared you like one of its kind MTech program which we are running here at MNIT Jaipur, and I may be wrong, but to my knowledge, in India there is no program which talk about electricity markets in depth. So, like, there is no PG program where electricity markets are being taught to this particular depth. So, yes, I think the MTech program's name is Power Systems Management. So, we are running that. And in MNIT, we have three PG program. One is, like the traditionally or very old, the very first MTech program, MTech in Power Systems. Then we have Power Electronics and Drives, and we also like for about different electricity markets, what are the regulations and policies, how these are being defined, uh, risk management we discussed basically, and planning of the system planning related issues, tariff design related issues, and like what are the different issues in deregulated power system or smart grid. So all of those aspects has been covered in the MTech program in power systems management. So I have shared a scheme for with you, and there are a lot of books available in that scheme. Like with each course, we have provided a certain book. So you can, like, somebody was asking that provide a list of books, so it is there. And you can, with respect to, like, the course of like our power system operation, that is, I think, optimal operation and control of power system. You can see there are certain books about markets, and there is a course, so it has certain books. So a lot of reference material is there, so you can follow that reference material. uh, okay. Apart from that, like, any doubts? I was waiting, that's why I started discussing something else. Any doubts so far? So now let's talk about another factor, which is called LODF. Okay, so it is basically line outage distribution factor. Okay, line outage distribution factor. So let's say I have a network. Some line is connected between node L and M, and let's say some line R and S is basically has a outage. Okay, so this line was existing currently in the system. So if this line is RS line is part of the system, then we can say that our X matrix is well defined. So this X matrix we have already calculated, including that particular line RS. And let's say while operating in the system, we basically, this line becomes like, because of some fault or overloading, some circuit breakers opens this particular line. So how the power flowing in this line will be redistributed over the entire network, because this power now will no longer go in this particular direction because of the outage. So this power will go to this line, and if some other lines are there, it will go into those lines. So in generalized way, I'm saying in line LM, this line will go or start flowing to those particular lines. So that is defined by line outage distribution factor. So this is defined by a line outage distribution factor. Okay, so let's talk about that, because we have discussed that ATC depends upon system conditions. So system conditions also includes line outages. So if line is no longer exist, then it will also affect the ATC. Okay, so it is also limited by effect of the line contingencies. So line outage distribution factor can be defined or can be used to calculate that in cases of the contingency. So if there is any contingency, we can use this factor. It is again a linear factor. So after a line outage, the power flowing in that line is redistributed among the remaining lines in the network. And this factor gives that how much of that initial power which was flowing in line RS will flow into other lines. So it is basically like change in flow of line LM, and because of the outage in line RS. So let's say initially the RS PF RS was the power flow. If I multiply it with the LODF factor, I will get the change in flow in the line LM. Now, how we can use this particular to basically get the ATC calculation? So you know that okay, this is the formula for LODF. So I will note basically use it. It's it will take a lot of time, 2 hours at least, if we start using LODF to calculate the uh, ATC. But I already explained you, so you can basically do it. If you have any doubts, you can always reach out to me. So for a transaction between bus, now this has been defined. Now X matrix gives the network initial network information. All of a sudden, a line has been out. There is an outage in the line, and we have to instantly calculate the available transfer capability. In that case, what will happen, that ATC is nothing but the capability between node I and let's say some node J. So how much power I can transfer or basically withdraw. So what is the power transaction Ij or the maximum power transaction Ij I can perform here between node I and J. So what is the power transaction is can be performed. So if you see, let's say if I'm imposing this power transaction, the X matrix basically is include line RS as well. Okay, so X is basically included line RS. So for X matrix point of view, there is no line outage in the system. So RS is still part of the matrix. So if I transfer some power, that power will start flowing here as well. So because of this transaction, some power change in power flow in line RS will happen because of transactions IJ. Okay, and then this line is outaged, and because of this transaction some change in power flow, so let's say some initial power flow. Okay, so some initial power flow note was already there in the line, then because of this transaction some change will happen in line LM power flow because of the IJ transaction, and then some change will happen in particular power flow of line LM because of the RS outage. Okay, and that RS power is also included the new transaction IJ, because this is RS plus the new power flow because of the new transaction. So just keep it in mind and try to apply the logic. So the transaction between bus I and J change in power flow in the line RS will be this. So I can say the power flow new in line RS will be power flow initially in line RS plus delta PF new in RS. That is the new power flow. Okay. Now, if I calculate the power flow in line LM especially, it will be PTDF LM comma IJ, and these are basically the new transactions. So because of this transaction, this will be the new power flow in the line LM plus this is the power flowing in the line RS. So this is the power flow in line RS, and by multiply this LODF, I can calculate the change in power flow. So this is actually the total um, change. Okay, and initially some power was there, and this is the total change. So this will be the new power flow. And if I apply these ones and try to calculate, like if I put everything here and try to calculate, let me change the color of the pen. So if I try to calculate this and this, so this is I'm interested, this is I'm transferring from I to J. So what will be the power transfer between I to J, or the new transfer, and what maximum value it can take. So if I use these two formulas and put it here, I will get this as a PTDF max uh, transfer between IJ in line RM, and we are considering that there is an outage of line RS. So this is what it is. Now, because of this outage, we can calculate this factors. Then ATC will be this we have already defined earlier, that it is minimum of whatever is the power maximum. So this is from the basically already just without you can say it is without outage, there is no outage, how much you can transfer, and then with outage, so this is with outage, how much you can transfer. And so this is like, minimum of without outage, you can how much you can transfer between point A to point B, or point I to point J in this case. And if outage is there, then how much minimum power you can transfer from point I to point J. And the overall minimum of both will be the ATC in outage condition. So this is ATC under line contingency in RS. So this is available transfer capability under line contingency. So this is how we can calculate. Now, if we talk about like ATC using AC power flow method, so PTDF is a function of voltage and angle sensitivity in AC power flow model can also be formulated. Okay, so power transfer distribution factor in terms of voltage and angle sensitivities can be calculated. And generally, like Jacobian matrix and above sensitivities are used for calculation of AC PTDF. And those AC power transfer distribution factors can be used for the calculation of ATC, but they are complex and the formulas are also very complex in the nature. So generally, we prefer the DC models, like the formulas which we have used for the DC model. Then let's talk about the congestion management. So in between, we just calculated that. So that, like, if I go back my very previous slides, these were the steps of network access. So first of all, we need to calculate the ATC, what is the available transfer capability, and then we will apply the different methods. So we have calculated ATC, that how we can do. Then there are different congestion management methods. So we discussed that there are market-based methods and non-market-based methods. If I talk about non-market based method, it's basically type of contract, like which type of contract we are basic. Yeah. So I am talking about the non-market based methods. Here, based upon the type of contract, we can schedule or basically allow uh, uh, the use of network. So let's say certain contract is there, bilateral contract, long term bilateral contract, let's say like year ahead. And for those contracts, we will generally give higher preference. So those contracts will be provided that, okay, you are allowed. And if some capacity bottlenecks are coming, let's say congestion, let's assume there will be some congestion, then first of all we will allow the bilateral contracts which are long term in the nature, that okay, these contracts first of all will be realized. And if some then we will go for, like, day ahead market and subsequent market places. So this is how we basically decide that how we can provide or give the reservation in the existing transmission corridor if it is going to be congested. Then if some capacity is available, then we will provide that based upon first come first serve basis. So, like, like some initially emergency contracts, basically type of contracts has been fulfilled, then some new contracts, like, like week ahead, which are coming recently, okay, and like week to month ahead bilateral contracts are there. So whoever comes first, he will acquire the basically uh, capacity in the transmission corridor. So that is another way of doing it, like, first come first serve basis. That is another method. Another is pro rata method. Pro rata is like, proportionate method. So here what we can do is, like, suppose there are multiple transactions are happening between point A to point B, and all of those transactions are basically agreements. Basically, they request uh, corridor, that okay, I want to transfer power, let's say from northeast to Rajasthan. Okay, so I need certain corridor. So I will request that, okay, give me this much capacity in the transmission line. And if lines are congested, then in the proportionate of what we those transactions asked, we can basically provide the corridor, that okay, if somebody, let's say everyone, one person asked, like, I want to transfer 10 megawatt, another person asked, like, I want to transfer 20 megawatt. So, and the corridor is only there for 20 megawatt, then that 20 megawatt will be divided with the ratio of like 1 and 2. So one person will get, I think, 1 by 3. So that is 20 by 3, and another will get 20 into 2 by 3. But the issue here is we discussed that method should be robust, but pro rata method is not robust at all, because if we know with like continuous practice that this line is always, or the network is always congested for my transaction, so I will ask for a like higher quantity, and I'm sure that okay, this corridor is going to congested, so based upon the proportionate sharing, they are going to, or the system operator is going to reduce whatever I have asked, and in that case I can secure my true um, commitments. So that pro rata method has those difficulties. And the last resort is curtailment, that we can basically always curtail certain demand, that okay, this demand cannot be supplied because we cannot do anything. So like there is curtailment is basically last resort, like we cannot do any modification in the system, we cannot redispatch, and all the methods has been applied, and still if we are not able to supply certain demand, we will have to curtail that one. So that is the like last resort, so no market based method. Then some market based methods are also there, where the first one is explicit auctioning, where we auction the corridors, that okay, this corridors basically like the transactions are like buyer and sellers, they can bid into a certain corridor, they can participate in the auction and acquire the rights of that corridor. Okay, so they can like if rights has been acquired, then you can use that corridor. So that is explicit auctioning. Usually like in European market, node pool, they perform this explicit auctioning. In India we perform all the non market based methods as well as few market based methods. But yes, we have type of contract as well. Long term contracts are given preference. Then after that, for the short term contracts, first come first serve is given preference. And pro rata is no, I think, not being used any longer, but curtailment, yes, final last resort is for everyone, curtailment is also being done. Then another method is nodal pricing. So this we have already discussed. Nodal pricing is nothing but your DC or ACOPF. That whatever is the limit of the each line, it is already part of the optimal power flow problem, and by doing so, we are basically scheduling our generators and utilizing the entire network in optimal way possible. So, and the outcome of this OPF will is basically the outcome is LMPs. So those are basically nodal prices. So that method we have already discussed. Then some zonal prices method is also there, where what we do is, instead of like providing price for each node, we divide the entire region into one zone and ask for a same price. Okay, so zonal pricing based methods are also there, and those zones are defined by the power flow in the tie lines. So if you see in India, if you look at the, like go or visit some power exchange website, there are different price zones available. Okay, so different prices are given, and those zones are defined based upon the congestion between the two zones. So let's assume there is a Rajasthan, and let's assume some Gujarat is connected with the transmission line. If that transmission line is congested, uh, and okay, we also discussed that if there is a congestion, price difference will come. So in India, we follow zonal pricing. Like in the entire Rajasthan, the prices will remain same. So that zonal pricing we use, and the prices are basically deviated by the like inter zone tie line connection. If that tie line connection is congested, then because of that congestion, power is must be flowing from one zone to another zone. So from where the power is flowing, that is cheaper zone and other zone is basically expensive. Okay, so the prices should also follow that particular direction. So like there will be price difference, and then we perform generally price area congestion management. So I will talk about this. Redispatch, it's basically a kind of uh, you can say OPF as well. Like, so in optimal power flow, we perform the like all the generators and everything, but still it's a let's say we have performed in day-ahead fashion that okay everything is fine, but in real time again some scenarios has been changed. In that case, let's say some line outage is there, and that line outage created some congestion. In that case, we have to redispatch the generators. So we will not perform again the OPF, we will redispatch. So the in OPF, the objective will be redispatch instead of minimization of the cost. Okay, so what is the redispatch cost? So that will be minimized. Counter trades, we already discussed that if some congestion is happening from area A to area B, we encourage counter trades from area B to area A so that reverse flows can reduce the congestion. But it is very difficult as well. Like, whatever is the true nature or the behavior of the system, counter trades will also be like, already part of are there, and you cannot exercise or like put counter trades, but yes it is one of the method we can also do it. So in OPF, we have discussed like in nodal pricing is basically OPF. OPF can be of AC or DC, and transfer power optimally, and consider the network constraints. So like network constraints has been considered already, so there will be no congestion. Everything will be on the like within the limits, and the byproduct is LMP, nodal prices. Nodal LMPs are there, and they are basically we already discussed that they are the Lagrangian multiplier of the power balance equation. And we can have different objectives for the OPF. Generally, like this cost minimization and social welfare minimization gives you the LMP, and rest of others are not. But for the congestion management, sometimes we have a objective of loss minimization. We already discussed that redispatch is one of the methods, so we can have minimization of redispatch cost. If some adjustments needs to be done, what is the minimization of total adjustment? Some curtailment has to be done. Then which loads to be curtailed? That is also a question mark. So minimization of the load curtailment, that will give you that okay which loads should be curtailed, so that minimum curtailment is possible. So these objectives can be performed to basically provide the congestion management. Uh, if a line is congested, it gives you line shadow price. Okay, so what is a line shadow price? Line shadow price is defined like as given in the slides, the rate of decrease of the optimal operating cost with respect to the increase in the capacity of that particular line. So let's assume I have a line, and other parts are as well. It's the same example 1 to 2, and the power is 30, and maximum limit is also 30. Okay, and in this particular case, let's say the capacity was how much? Let's say 150. So out of 150, how much will be provided by? Some will be provided by this generator, and some will be provided by this particular generator. So we can supply this 150, and to keep it 30, you can calculate this example we have already discussed. Okay, so what we can do is we will increase the line limit. So whatever is this limit, instead of 30, we will make it 31. So the PF max will be changed by certain value, and let's assume it is 1 so that we don't have to divide anything. In this case, we will check for the cost. So if instead of 30, if it has been increased to 31, this, let's say this is the cheaper generator and this is the costly generator. So obviously, if this line is been relaxed, we can basically inject more cheaper power and basically reduce the costly power. In that case, the overall optimal cost will be reduced. So this optimal cost will be less and this cost will be more. So whenever the line is, let's say, only 30 and let's say the increased line is limit is 31, including both of these two values, this cost will be more and this will be less, and the difference is basically divided by this whatever how much relax we have done is called line shadow price. In general, if we look at our formulation, we have done some programming and hands-on as well. So as we have defined that LMPs were basically the Lagrangian multiplier with respect to the power balance equation. Similarly, the so the capacity of the line, so whatever is the line capacity, capacity, so Lagrangian multiplier we have, and if we can take a partial derivative with respect to the capacity of the line, that can give you the line shadow price. Okay, so generally we define it as like incremental change in, or basically it's the change will be decremental. So decremental change in optimal operating cost for a 1 megawatt increase in the line capacity. So that is line shadow price. Okay, this particular example we have here. So let's say the cost of here is 10, cost of here is 20, the capacity is 100, capacity is 20, 50 megawatt is the load, and line limit is 80. So obviously the generator 1 will provide 50 megawatt and generator 2 will provide 0 megawatt. Now if I so the PF max here considered is 80 megawatt. Now if I increase my PF max to 81, 1 megawatt extra, still the load is 50 only. So in that case, the schedule will remain same, and change in cost. So LSP is basically uh, change in cost, and that will be equals to 0. So that's why LSP is 0 for this particular example. Now let's say the load is 90 megawatt and line limit is, so here the PF max 12 is 80. So in that case, the generator 1 will provide 80 and generator 2 will provide 10. And if the PF max is made equals to 81, then obviously the line is more. So we will try to have as much possible as from this generator 1. So we will have a 81 capacity here and 90 capacity here. So this LSP is basically change in cost. So earlier cost was 80 into 10. So the cost here is basically 80 into 10 plus 10 into 20, and cost here is what, 81 into 10 plus 9 into 20. Okay, and the difference between cost 1, so whatever is the cost 1 minus cost 2, that will be your LSP. Okay, so we can define it like this. Any doubts so far? Then for the same example, we generally calculate network rent as well. So network rent is basically, let's say, assume what will be the LMP here, lambda 1, it will be 10, and lambda 2, it will be 20. Okay, so network rent will be basically how much is basically product of LMPs and power withdrawal at every node. So network rent is basically, let's say, how much is loads are paying. So they are paying at the price of lambda 2 into 90 megawatts minus how much has been paid to the generators. So generator 2 is supplying how much? 10 megawatt. So it will be at lambda 2 into 10, and then plus lambda 1 into 80. So we know that lambda 2 is 20, lambda 1 is 10. So it will be basically network rent will be, so 20 into 19 कितना होता है 1800 minus lambda 2 was 20 into 10 is 200 and 800. So we will get 800 of network rent. So whenever there is a congestion, some line shadow price will come, and if you look at the line shadow price, it is 10. So you can also say the network rent. Basically, the network rent is LSP of line LM into the actual power flow or maximum power flow capacity of line LM. So LSP was 10 and the power flow capacity was 80, so it is 800. So if some congestion is there, obviously congestions are there in the system. In that case, loads will pay as per the, let's say if you are talking about this particular method, loads will pay as per the LMP. So some money has been paid, and in this particular case we have only one load, so it is paying 1800. Then generators will get money at per their LMP. So generator will, one will get at the LMP of 10 and generator 2 will get the at the LMP of 20. So the difference is basically like, generators, we only paid 1000 to the these two generators. So 800 is left on the table. Nobody is, like loads has been paid, and then it has been paid to the generators. Now 800 is on the table. What we can do with this particular 800? Who should get it? Any system operator, but system operator is a non-profit making entity. It cannot make a profit out of it. Otherwise, what it will do is, it will, let's say the actual line limit is 80, but he knows that if I restrict the line limit to a very less amount, and in that case, and create congestion. So like, actually there is no congestion, but the system operator will create congestion by, supplying any lesser limits in a few of the lines, as we discussed. Like, Satya asked, like it by this means most of the lines are underutilized. Yes. So let's say 200 megawatt is the line limit, and the actual power flow is only 70 megawatt. So the system operator knows about it. So he can say that no, this is not 70, it is 60 megawatt. So in that case, the OPF will take care of that 60 megawatt as a line limit, and there will be congestion. And if there is a congestion, there will be some line shadow price. And if there is line shadow price, some network rent will be created. But TSO should not do that. So, but in this case, let's assume everything is true. Nobody is artificially manipulating the line limits and creating the network rent. So, obviously, this money will go to the system operator or the network operator, and but this money can only be used for relieving the congestion, because this is congestion money. We are getting this money because of the congestion, so it should be used to relieve the congestion. And how can we relieve the congestion? Anyone? What is the long term solution to remove the congestion? Yes, so capacity elevation methods, and the short term methods are still basically, you know like curtailment and redispatch, but those are not solution. So network reconfiguration, like we are talking about transmission, so generally we cannot, we don't have that option of reconfiguration of the network. In distribution we can do, but in distribution, um, congestions are very rare. Okay. So we can reduce the power flow. Yes, so this money will be used to build new lines. The question is whether it should be a parallel line or a line somewhere else. That is a very big question mark. Because even if you build a parallel line, uh, the power flows will be as will again follow the laws of physics. Okay, so let's say one line is there which have a very low reactance, but as well as very low rating. So let's say 50 megawatt is allowed and reactance is very low for that particular line. If I build a parallel line to that 50 megawatt capacity line and let's say 200 megawatt line, what will happen in that case? Will power be directed to 200 megawatt line? No, it will let's say if x is less for 200 megawatt line, then only power will flow in that particular line, but still that 50 megawatt line is still there. So we have to do transmission expansion planning and decide that where should I build a new line so that my congestion can be removed. Okay, so it is basically planning decision because constructing a new line also takes too much time. So it's like years of planning and execution. So for years we are taking to build a new line. It's not short-term solution. We have to consider the system growth, that how much the load will be in the future, let's say 5 years down the line, because if I build a transmission line, it is going to be used for another 20-30 years, right? So and even more than that, we have never seen decommissioning of the line. So we will there will be lot of time is available, lifetime is very much high. So we will do a long term system planning, that okay, this is the existing system, and if I build a new line, and this will be the load scenarios, that okay, these load centers will the power consumption will increase in future. And as per the government policies, this is basic like different power plants are being coming. Okay, and government has some vision that okay, we need to build power plants of certain type in certain location or geographical area. So all of those scenarios has to be considered, and under those entire scenario consideration, we can do some system planning, that okay, we have to build a new lines, and this should be the location, this should be the capacity. So all of these are basically done for that. So network rent can be used uh, for that to build a new lines. Apart from that, obviously, like we have I think we have discussed network pricing as well. So if new line is there, this network rent will not be enough to build new lines. It is a very big project, and a huge amount or capital is needed to build new lines. So like if you say that okay, we will accumulate network rental over time and that money can be used, no. So whatever is the capital of the new lines, we can use this money to some extent, and whatever is the remaining, that remaining money will decide the wheeling charges or uses of that line. So somebody is using that line, how much it has to pay. So like as a discom in Rajasthan, if it is buying some power from a producer in north east, like some hydropower plant there, then it is using the network from north east to the Rajasthan. It has to pay certain wheeling charges. So those charges are basically, I think, discussed by Professor Bakar as well, like in the network pricing. So those are basically a network pricing, and that network pricing is to compensate the cost of new lines and building the new lines. So if you have any more doubts, please ask. Then we have another session at around at 2, uh, that will be about security constraint, unit commitment, and how we can use AI. So that's a very good question, Satya. How fact devices change these all these calculations? So fact devices can alter or reroute the power flows to some extent. So let's say like capacity elevation I have to do, like I have to increase the capacity of a particular line. If I can, I'm able to change the reactive power flow, I can increase the active power flow. So if I can reduce the reactive power flow, I can increase the active power flow of that particular line. So I can, yes, I should, generally the system operator use fact devices to increase the capacities of the line, and are basically to increase the ATC of the particular lines. But they are short-term solutions, not long-term solutions. So, like for short-term and for a limited capacity, we can do. So, yes, fact devices are very much helpful in that case. But long-term solution is building the new network. Okay, new transmission lines needs to be built, but the economics behind everything is the same. Like even though if we use the capacity fact devices, they those are basically part of real time system operation. So whenever there is a like in real time, if some congestion is there, then capacity elevation can be done with the help of fact devices, just to maintain the security of the entire system. So it is in the hand of the system operator. Yes, so yes, we can use, and we can use the fact devices. Any other question? How RE wind curtailment is handled in electricity markets? So as I discussed, like we discussed three different options earlier. Okay, that first option was like in the very beginning of the system, when we were basically encouraging RE or wind basically. So they are just injecting, and they will get, basically getting paid at a regulated tariff, and it was risk free, but uh, not profitable as compared to if there are more opportunities of making more profit. So then we discussed that if perfectly competitive market is there, uh, wind or renewable can participate in the markets and face the deviation charges or penalties basically if it is deviating from the schedule, and that is basically the market. Now curtailment is not in the market. Whatever is the outcome of the market, we just follow that. Curtailment is last resort, as I discussed earlier as well. Like curtailment is always last resort option. So if security is basically compromised, and the system operator will take the decision of the curtailment. Okay, so in real time, let's say in the afternoon time, lot of solar is coming into the system, and if it is affecting the entire system, then in, let's say, in particular corridor, a lot of power is flowing, and we want to restrict that power flow, then it can ask the producers, renewable producers, to curtail certain power. So yes, system operator do this, and that is because of the security concerns and to maintain the entire system. But in the market is fine. Market is basically like it has been committed, it will be like supplying that much power. Any deviations are there, then it will be curtailed. And in real time, if all of a sudden let's say demand goes down, okay, in that case renewable is lot of injections are happening, uh, it will ask other conventional generator as well to curtail the power. So it's like for everyone. So that is, I think, I hope I am able to answer you. Curtailments are last resort options. In real time balancing market we do, and it is in the hand of system operator. So he has to maintain or manage the system. Any other doubt? So in the afternoon session, we will talk about AI, like how we can use AI, what are the different methods, what are the different applications. So those are interesting sessions. So we will resume at 2. Thank you very much. If you have doubts again, you can always reach out to me. We can also discuss on the WhatsApp group, but I usually not prefer typing, so you can call me. I will prefer explaining verbally. Thank you.